Okay, so now let's talk about probability of an event. Let's talk about the probability of an event. Let's see what that is. Now it says that let S be a sample space associated with the experiment examining 3 consecutive prints produced by a machine and classified as good, meaning non-defective, and bad, defective. And we may get 0, 1, 2, 3, 0, 1, 2, or 3 defective pens as a result of this examination. Let S be the sample space associated with the experiment examining 3 consecutive pens produced by a machine and classified as good and bad. So we have some experiment which is basically examining 3 consecutive pens, examining 3 consecutive pens produced by a machine and classified as good meaning non-defective, or non-defective, and bad meaning defective, So this is the experiment that we have. So we may get 0, 1, 2, or 3 defective pens as a result of this examination. Okay, so we may get 0, 1, 2, or 3. Well, that makes sense. Yeah, of course you may get 0 or 1 or 2 or 3 because the total number of pens is 3 basically. So you may get basically 0, 1, 2 or 3 defective pens as a result of this experiment, of this examination. Okay? Now, a sample space associated with this experiment is a sample space associated with this experiment is S is equal to basically so you have let's write the sample space as this. So you have 3 consecutive pens, meaning that the first pen and the second pen and the third pen, and the first pen you may get a bad one or a good one. The second pen you may get a bad one or a good one. The third pen you may get a bad one or a good one. Now combining these two together, you will get BB or BG or GB or GG, and then combining these four with these two, you will get basically BBB, you will get BBG, you will get BGB, you will get BGG, you will get GBB, you will get GBB, you will get GBG, you will get GGB, and you will get GGG. So you will get basically all of these outcomes as a result of this examination, and that will be your sample point. The sample space. So you have BBB, you have BBG, you have BGB, you have GBB, you have GBB, which is here, you have BGG, you have GBG, you have GGB, and you have GGG. So that's basically the sample space associated with this experiment. Now the probability, they have basically assigned some probabilities to each of these outcomes. So the probability of each of these outcomes has been given as 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, and 1/8, and they are basically valid in the framework that we talked about, in the framework of axiomatic probability. They are well valid. I mean, each of them is greater than 0, less than 1, and the sum of them is 1, so you have no problem there. Now we have an event A. We have an event, let event A be. So we can define some event A as, for example, there is exactly one defective pen, and event B, there is exactly one defective pen, and event B as there are at least 2 defective pens. There are at least 2 defective pens. Hence you can write A as there is exactly one defective pen, so you would go with 1B basically. So that would be, for example, BGG, for example, BGG, and then you would have GBG, you have GBG, and then you have GGB, and then you have, that's it. And B, you can write it as there is at least 2 defective pens. So that means that you would get BBB, then you would get basically BBG, then you have BGB, then you have at least 2 defective pens, so GBB, then you have basically, and that's it. So you have 4 outcomes here and 3 outcomes there. Now P of A, the probability of the event A occurring, is sigma P of omega of I is equal to sigma P of omega of I for each, this means for each omega of I belonging to A, which means that it's equal to basically P of BGG Okay, so now we said that P of A is equal to sigma of P of omega I, as I, for example, goes from 1 to 3, you can say, as I goes from 1 to 3, for each omega of I belonging to A, meaning that you get P of BGG, for example, plus P of GBG plus, for example, P of GGB, which is equal to 1/8 plus 1/8 plus 1/8, which is equal to 3/8. And P of B is equal to sigma P of basically omega of I for each omega of I belonging to B, as, for example, I goes from 1 to 4, for example, right? And so that is equal to basically P of BBB plus P of, for example, BBG plus P of BGB plus P of GBB plus P of GBB, which is equal to 1/8 plus 1/8 plus 1/8 plus 1/8, which is equal to 4/8, which is equal to 1/2, right? So let us consider another experiment of tossing a coin twice. So let's consider another experiment. Okay, so now let's consider another experiment of tossing a coin twice. So the experiment is, we have the experiment of basically tossing a coin twice. So the experiment of tossing a coin twice would be, the sample space for this experiment would be basically H would be HT, would be then TH and TT. And let the following probabilities be assigned to the outcomes. Let the following probabilities, that's not an easy really, probabilities be assigned to to the outcomes, which is P of, for example, HH is equal to 1/4. P of HH is equal to 1/4, and P of HT is equal to, for example, 1/7, and P of TH is equal to 2/7, and P of TT is equal to, for example, 9/28. P of TT is equal to 9/28. So if that's the case, let's see. Okay, so now each of these probabilities is some value between 0 and 1, and the sum of these values is basically 1/4 and 1/7, 2/7, 9/28. So if I take the LCM as 28, for example, I get 7 plus 4 plus 8 plus 9, which is equal to 11 plus 17, which is equal to 28/28, which is equal to 1. So the values of probabilities that we have assigned to these outcomes, there is no problem with them. And this is actually, I suppose, this is actually the concept that we talked about before, that, for example, in an experiment, basically what we did before was that we said that we made the assumption, that all outcomes were equally likely to occur. So when all outcomes are equally likely to occur, then of course over here you have to, since you have made this assumption, you have to write P of HH, for example, is equal to 1/4, because the number of those events is equal to 4, or the number of those outcomes. And then you need to write, for example, P of HT is also equal to 1/4, and P of TH is also equal to 1/4, and P of, for example, TT is also equal to 1/4. And so when you add all of these together, you will get 1/4 plus 1/4 plus 1/4 plus 1/4 is equal to 4/4, which is equal to 1, which of course makes sense. But then we have made the assumption that all the outcomes were equally likely to occur, meaning that you cannot assign a different value to this possibility than to the other one. Okay, so here what we did was that we made the assumption that all the outcomes were equally likely to occur. But here we don't have to make that assumption, meaning that, for example, you can consider the probability of this outcome happening as 1/4, this one as 1/7, 2/7, and so on and so forth. The only thing that's important is that the sum of all of those outcomes is supposed to be equal to 1. Okay? Let me close my window. So the only thing that needs to happen is that the sum of those probabilities is equal to 1, and none of those outcomes is nowhere less than 0 or greater than 1. So that's basically the only thing that we need to do. And that way what we get to do is that you can have outcomes of the same experiment which may have basically different probabilities of occurring. For example, in this case, you can see that, for example, 1/4 is of course a greater fraction than 1/7, right? Because over here is the denominator is greater, so this one is greater, and the numerators are the same. So since that's the case, so that means that then the probability, for example, of this event happening is of course greater than the probability of this event happening. And we can of course compare each of these probabilities back and forth. You can do whatever you want, but there are basically situations where, for example, actually most of the time, for example, the coin that you use is most of the time biased towards, for example, no matter how symmetric your coin might be, no matter how controlled your situations are and everything else, in that specific situation, what you will find is that basically the coin that you're using in order to perform the experiment of tossing a coin, for example, 1,000 times or 2,000 times or 3,000 times, you will find that your coin is more, for example, biased towards heads than tails. So then you will basically, based on your experiments, you will keep experimenting with the coin, and then you assign a higher probability to, for example, heads than tails, or whatever the case might be, basically. And that way you will, basically the result, the overall result of your calculation is going to be, of course, higher. The accuracy of the result of your calculation is, of course, going to be higher. So now this basically this assignment satisfies the conditions of axiomatic approach over here. Now let us find the probability of finding, for example, some events in this case. So, for example, you want to find the probability of the event. You want to find the probability of the event E, which is, for example, both the tosses yield the same result. Both the tosses yield the same result. So what that means is that basically from among all of these outcomes, you would get basically, for example, E would be equal to either HH or TT, and that's basically the two outcomes that would favor this event. So now, based on what we said before, you can say that P of E, the probability of event E happening, is equal to basically sigma P of omega of I for omega of I for all omega of I belonging to the set E, for example, to the set E, or yes, belonging to the set E or belonging to E. So that would be basically the sigma of P of omega, basically P of omega of, so that would be, for example, P of HH. That would be the probability of HH plus the probability of TT, and that would be equal to, for example, 1/4 plus, for example, 9/28, which is the same thing as 7 plus 9, which is equal to 16/28, which is 8 divided by 14, which is 4 divided by 7, that's 4/7. That is 4/7. Now for the event F, for example, in the exact same situation, let's define some event F, which is exactly 2 heads. Exactly 2 heads. And for this event, you would have, for example, some set over here, like which is basically HH. And then again, P of F over here would be equal to sigma of basically P of omega of I for all omega of I belonging to the set, for example, F. And that means that basically you would have to basically write P of HH, which is equal to, in this case, for example, 1/4, and that's the probability of event F happening. Now the next thing that we have here is the probabilities of equally likely outcomes, which of course again we can do it here as well, but then we can simplify things a little bit, not to basically we can so let's see how that goes. So let's see the probabilities of equally likely events. The probability of equally likely events. So the probability of equally likely events, let the sample space of an experiment be, let a sample space of an experiment B, S is equal to, for example, omega 1, omega 2, omega 3, all the way up to omega of n. Let all the outcomes are equally likely to occur. Let all the outcomes be equally likely to occur. That is, the chance of occurrence of each simple event must be the same. That is, the chance of each simple event must be the same. That is basically P of omega of I is equal to P for all omega of I belonging to the set S, where 0 is less than or equal to P is less than or equal to 1. So here we say that let a sample space for an experiment be, for example, S is equal to omega 1, omega 2, all the way up to omega of n, and let all the outcomes be equally likely to occur. That is, the chance of each simple event must be the same. Okay? And what that means is that the probability of omega of I or P of omega I is equal to P, lowercase p, for all omega of I belonging to S, where P is less than or greater than or equal to 0, or less than or equal to 1, right? So that makes sense. Now, since basically sigma of P of omega of I, since sigma of P of omega of I is equal to, as I goes from 1 to n, is equal to 1, that is P plus P plus, that is P plus P plus P plus n times plus P n times is equal to 1, then that means that n times P is equal to 1, which means that basically P is equal to 1 divided by n. Which means that P is equal to 1 divided by n. Now, let S be a sample space. Let S be a sample space, and E be an event, such that n of S is equal to n, such that n of S is equal to n, and n of E is equal to m, and n of E is equal to m. If each outcome is equally likely, if each outcome is equally likely, then it follows that P of E is equal to m divided by n, which means that the number of, so basically this is n on n of S, which is equal to n, and n of E is equal to m, and we have written this as m divided by n, which is the number of outcomes favorable to E, the number of outcomes favorable to E divided by the total possible outcomes, divided by total possible outcomes, divided by total possible outcomes. Okay, so to recap what we have here is not that actually simple. So let's review that. Okay, so to review, basically we said that let the sample space of an experiment be, for example, S is equal to omega 1, omega 2, omega 3, all the way up to omega n. Okay? And let all the outcomes be equally likely to occur. That is, basically the chance of each simple event must be the same, which makes sense. That means that basically P of omega of I is equal to P, some some value, for example, because all of them are equal as we argued here, for each omega of I belonging to S, where basically P is greater than or equal to 0 and less than or equal to 1. Now since sigma of P of omega of I as I goes from 1 to n is equal to 1, that the sum of all of those probabilities is equal to 1, which means that basically P plus P plus P n times is equal to 1. That means that then n times P is equal to 1, which means that P is equal to 1 divided by n. Now let S be a sample space and E be an event such that n of S is equal to n, meaning that the number of the elements of S is equal to n and the number of the elements of E is equal to m. So if each outcome is equally likely, then you can argue that you can say that it follows that basically P of E is equal to basically m, the number of outcomes favorable to E, divided by the total number of possible outcomes. And here you can write directly n, because basically all of those outcomes are equally likely, right? And that gives you basically the number of outcomes favorable to E divided by the total number of the total possible outcomes. So that's basically that. Now, of course, in case you didn't, it's always a matter of using, for example, some formula in some, basically using some concept in some example in order to understand it, which we will come to shortly. Now, the next thing that we have here is called the probability of the event A or B. The probability of the event A or B. The probability of the event A or B. So let us now find the probability of event A or B, which is basically in the previous videos we said that basically the event A, basically A or B, we could write it as, basically A union B, right? So that means that when you want to find the probability of this event, you can just simply write it as the probability of A union B, right? So that you can do. And so if, for example, let A be equal to, for example, HHT or HTH or THH, and that is basically all of the outcomes related to A. And let B be equal to HTH and THH and THH and HHH. Be two events associated with tossing of a coin thrice. So let A and B basically be two events associated with tossing a coin thrice. Now clearly A union B is equal to basically HHT So you have basically HHT, you have HDH, you have THH, HDH, so that is already covered, and then THH is already covered, and you have HHH here. So you have 4 outcomes here. So A union B is basically this set over here. Now, P of A union B is equal to P of HHT, P of HHT plus P of HDH plus P of HHH. Plus P of HHH. Now, if all the outcomes are equally likely, if all the outcomes are equally likely, then you can say that basically P of A union B is equal to, then for example, so here we have each of them, we have to assign basically 1/8 to that, because when you throw a dice basically thrice, you would get 8 different outcomes as a result of that experiment. So each of them would get a 1/8. So over here, then P of A union B would be basically 1/8 plus 1/8 plus 1/8 plus 1/8, which is equal to 4/8, which is equal to 1/2. Also P of A, which is basically P of basically this event here, P of A is equal to basically P of, for example, HHT plus P of, for example, HDH plus P of THH, which is, well, of course, equal to, which is of course 1/8 plus 1/8 plus 1/8, which is equal to 3/8. And P of B is equal to basically P of HDH is equal to P of HDH plus P of THH plus P of HHH, which is again the same thing as 1/8 plus 1/8 plus 1/8, which is equal to 3/8. Therefore, P of A plus, therefore you can say that P of A plus P of B is equal to 3/8 plus 3/8, which is equal to 6/8, which is equal to basically, well, 3/4, which is equal to 3/4. So now it's clear that P of A union B, we got it as 1/2. So P of A union B, we got it as 1/2. Therefore, you can say that P of A union B is not equal to P of A plus P of B, right? The points HDH and THH are common to both A and B. So basically over here, if you go to A and B, that basically the intersection of A and B would be HHT, so no HDH, so you can see HDH here, HDH here, and THH, THH, and THH, THH. So these are common to both of A and B. So HDH, THH, HDH, and THH are common to both A and B, right? Are common to both A and B. In the computation of P of A plus P of B, the probabilities of points HDH and THH, that is the elements of A intersection B, are included twice. So over here, I mean, basically once you're including this HDH, for example, in here, and again you're including that in here, and again the same thing you're doing for this one for both of these probabilities, and so the basically, and that results in this being being not an equality, right? So now, in order to get that to get over that problem, what we need to do is that we need to basically subtract the probability of basically A intersection B. So when we have basically what we have here is A intersection B, if we take out the probability of these two from the sum, I suppose this becomes an equality. So let's see how that goes. Okay, so now let's see how we can take those 2 points, those 2 sample points out. So we said that the points HDH and THH are common to both A and B, and in the computation of P of A plus P of B, the probabilities of these 2 points are, that is, the elements of A intersection B are included twice. Thus, to get the probability A union B, we have to subtract the probabilities of the sample points in basically A intersection B from P of A plus P of B. So what that means is that, so when we add, basically when we take the so when we basically over here we have basically A and B. So it's pretty simple. We can figure that out. So we have A and B. So in A and B, these two are common between the two. Are common between the two events, right? So that means that if I were to calculate the probability of A union B, I would have to basically and if I were to write it as P of A plus P of B, you can see that the probability of basically, basically P of HDH is calculated here. Also the probability of THH is calculated here. And the same thing is again calculated here. So that means that I have to, if I want to calculate the probability of A union B, I have to write it as this as probability of A union B as equal to P of A plus P of B minus the probability of A intersection B, because A intersection B is nothing but basically HDH and HDH and HD basically THH, and well, the probability of then A intersection B would be basically the probability of HDH plus the probability of THH, which is exactly what I want to subtract. The probability of these two I want to subtract. So that's going to be my formula, right? So then you can say that the probability of A union B, so then you can say that the probability of A union B is the same thing as probability of A plus the probability of B minus the probability of A intersection B. I think that's basically what we have here. So here it says that basically in the computation of P of A plus P of B, the probabilities of point HDH and THH, that is the elements of A intersection B, are included twice. Thus, to get the probability P of A union B, you have to subtract the probabilities of the sample points in A intersection B from basically P of A plus P of B. So then we can say that P of A union B is equal to P of A plus P of B minus sigma P of omega of I for all omega of I belonging to A intersection B. So you can write it in this way as well, of course. You can write it as P of A union B is the same thing as P of A plus P of B minus sigma P of omega of I for all omega of I belonging to the set A intersection B. Which is the same thing as, of course, what I've written over here. Thus we observe that basically the probability of A union B is equal to the P of A plus P of B minus P of A intersection B. So that's basically the formula that we were looking for. So that means that in general, so that means that in general, so there is okay, so now let me go up here and give myself some more space. 452. Okay, so then you can say that in general, if A and B are any two events, if A and B are any two events associated with a random experiment, associated with a random experiment, then by definition of probability of an event, then by the definition of the probability of an event, we have P of A union B is the same thing as sigma of P times omega of I think there is something wrong in here. Or maybe the P is supposed to be an uppercase P. I don't understand that. So let's see. So P of A union B is equal to sigma of basically P of omega of I. Let's write it this way. Well, what they have written is they have written it this way. Sigma of P times omega of I. This I would write as if this was basically a lowercase p. I would read this as P times basically omega, P times omega of I, which in which case this P would basically denote the probability of some event happening. For example, if there is some basically outcome, for example HHT, you give it some probability, for example 1/8 or whatever, then this probability you can denote it as lowercase p, right? As some lowercase p. But I'm not sure what they mean by this here, so let's see what they actually mean by this. So it's sigma p of, or p times whatever that is, omega of I, for all omega of I belonging to the set A union B. Belonging to the set A union B. So in order for this expression to make sense, so P of A union B is sigma of P of omega I for all omega I belonging to the set A union. This has to be uppercase P, I suppose, because otherwise it doesn't make sense really. So since A union B is the same thing as A minus B union with A intersection B, union with B minus A, I don't know how they've gotten that thing. So it seems that A union B is the same thing as A minus A, which means that basically if you have some basically some A over here and some B over here, let's say that you have some A and B over here, and A minus B would be this part over here, and A intersection B would be this part over here, and B minus A would be this part over here. And so A union B, of course, would be this whole part over here. So of course you can write that, meaning that you can write A union B is equal to A minus B union with A intersection B union with B minus A, which makes sense. In case you didn't understand this, let me do that again. Okay, so basically, in order to understand this expression or this equation here, A union B is basically, you can imagine using a Venn diagram. Venn diagrams are almost always the easiest way to understand these expressions, because you can see things graphically. Otherwise you would have to calculate and do all that sort of thing in which you might make mistakes, but basically using a Venn diagram you can easily see all of this. So for example, suppose that you have some set over here A and some set over here B, right? Now A minus B is this part over here. This is A minus B by definition. Now A B minus A is this part over here. This is B minus A by definition. And this part over here is A intersection B. and this part over here is A intersection B, and this part over here, all of this whole part is called A union B, right? So as you can see, A union B is the same thing as the union of all of these three things. The union of all of these three things, which is A minus B, union with A intersection B, union with basically B minus A. And so that's basically what we have written here. So that's basically what that means. Now since that is the case, we have basically, since that is the case, we have P of A union B. P of A union B is the same thing as basically the is equal to basically sigma P of omega of I. You can write that, and then I will explain what this expression means, or what this equation means. So in order to calculate basically the probability of A minus B, you can write it as sigma of basically P of omega of I, for basically as I goes from, for example, 1 to n, for all omega of I belonging to the set A minus B, right? That we understand. And also the probability of this part over here, A intersection B, P of A intersection B, that's basically, at the end of the day, this is just a set, right? This as for example this one, this is also just a set. So you can write it as sigma of P of omega of I, as for example I goes from 1 to n for all omega of I belonging to the set of basically A intersection B. And also basically to find the probability of B minus A, you can write that as sigma of P of omega of I, as I goes from 1 to n, for example, for all omega of I belonging to the set B minus A. So now I can put all of these together and just add them together, just add all of these together, because as you saw over here, A minus B, A intersection B, and B minus A are just simply disjoint sets, meaning that, for example, if you have your A over here and if you have your B over here, so over here you would have basically B minus A. Over here you would have, I'm sorry, this is A minus B. Over here you would have A minus B. Over here you would have B minus A, and over here you would have A intersection B. And as you can see, these sets have nothing in common. That means that if basically, and when you put all of them together, you will get A union B. So now in order to calculate the probability of A union B, I have to take the probability of this part plus the probability of this part plus the probability of this part, and since there is no outcomes that basically any of these two sets basically share, so then I don't have to subtract anything. I can just write, for example, P of A union B is the same thing as the probability of A minus B. So I can simply write this as probability of A minus B plus the probability of A intersection B plus the probability of B minus A. And I have already written them down all over here, which means that basically P of A union B is the same thing as basically this expression over here, sigma of basically P of omega of I for all omega of I. And of course I need to close my parentheses, for all omega of I belonging to the set, for example, A minus B. So that is basically one part. And I need to add to that P of A intersection B. P of A intersection B is basically then sigma of P of omega of I for all omega of I belonging to the set A intersection B. And I need to add to that the basically P of B minus A, which is this thing over here. So that's sigma of P of omega of I for all omega of I belonging to the set B minus A, for example. B minus A. Right? So that's basically what I can write. And so what that means is that so I can call this, for example, equation number 1. Okay, I want to get to the end of this part and then end this video, which will take us a few moments still, but we will get to the end of it. Okay, so that was basically equation number 1. Now, basically, also you can say that P of A plus P of B, this is P of A union B, right? Also, you can say that P of A plus P of B is equal to, well, you know that P of A is the same thing as, again, based on the same logic, you can write it as sigma of P of basically P of omega of I, where basically for all omega of I belonging to the set A, for example, that would be P of A. And P of B would be omega of sigma of P of omega of I for all omega of I belonging to the set B. So that you can say, you can use these two over here as well. And so you can write this as P of A plus P of B. You can write it as sigma of the same things here. Sigma of P of omega of I for all omega of I belonging to the set A, and add this to basically sigma of P of omega of I for all omega of I belonging to the set B. and or to the event B, you can say. Basically it's the same thing, which is the same thing as which you can write the same thing as for all omega of I belonging to A minus B union with A intersection B. Okay. So, and you saw over here that you saw basically previously using the Venn diagram, we showed that basically, let me do this Venn diagram down here because we need to basically keep referring to it. So in the Venn diagram we showed that basically if you have this set A, for example, and if you have this set B here, so this part over here you can denote it as A minus B. This part over here you can denote it as B minus A. And this part over here you can denote it as A intersection B. Right? So now, based on this, I can write A is equal to basically the union of these two sets, right? A minus B and A intersection B. So A minus B union with A intersection B, that would be basically the set A. So I can use the same logic over here. Make a screenshot here. So I can use the same logic here, and instead of set A, I can write sigma of P of omega of I for all omega of I belonging to basically A minus B union with A intersection B, right? So I can write that. And also the set B over here, I can write it as a union of this set and this set, meaning that I can write B is equal to basically A intersection B union with B minus A. So I make the screenshot again. Where did it go? Okay. So then instead of, for example, the set B, I can write the same thing over here, meaning that I can write basically the sigma of P of omega of I for all omega of I belonging to the set, and instead of B I can write A intersection B union with B minus A. A intersection B union with B minus A. I can use this set here. Now what happens is that then I can write so let me check if I haven't made any mistakes here. Here I have basically sigma of P of omega of I for all omega of I belonging to set A minus B union with A intersection B, and then the next thing would be sigma P of omega of I for all omega of I belonging to B minus A union with A intersection B. And then we need to do some algebra on this thing here, which would be basically here omega of I belongs to this set here. So that means that I can write this as omega sigma p of omega of I for all omega of I belonging to A minus B, plus that, plus that, plus that. Okay. So then, of course, you know that, for example, A minus B and A intersection B are two disjoint sets, meaning that they have nothing in common. Also, A intersection B and B minus A are again disjoint sets, and you can see that very clearly over here. You see A minus B and A intersection B are completely disjoint sets. And by the same logic, B minus A and A intersection B are completely again disjoint sets. So what you do is that is of course you can separate them based on the logic that we use basically in probability, right? Not based on the logic of sets or anything like that. Based on the logic of probability, I can write this as basically sigma of P of omega of I for all omega of I belonging to this set A minus B, right? And then add to that this set all the omega of I in this set as well, because they are actually together, but they are disjoint sets, so you can add them together. So then you can write this as omega sigma of basically P of omega of I for all omega of I belonging to this set A intersection B. Now of course you might argue that, well, I can simply basically come to the end of this discussion and just take some formula, for example, like get to the end of this discussion. Some people, including me in the past, I hated proofs. I didn't like proofs because I was not ready to go through the process of proving something. And, well, I mean, you could be right. Proving things is not easy. It takes a lot of steps, and then you have to just keep doing a lot of algebra and all those kinds of things to get to the result. And, well, the result is already there, so why would you prove it? But the point is simple, and the point is that this is basically mathematics. I mean, there is nothing, except for what we are doing here. There is nothing else on earth that you can call mathematics. This is mathematics. And this is how basically how you learn mathematics. And this is how, for example, when you go through these proofs and when you learn how to prove a couple of things that have been proved by other people, then of course that logic will be improved in your mind, and the logic will be basically kind of taken care of in your mind, and then you will be able to prove your own things. And that is basically the meaning of that is the meaning of becoming, for example, a mathematician. A mathematician is the kind of person who can do this kind of thing. Very simple. And of course, a mathematician, for example, goes on and does a PhD in some branch of mathematics, wherever mathematics takes him or her. But at the end of the day, a mathematician, what does he do? Or what does she do? They just sit and do this kind of thing all day long. And of course, if you don't enjoy this kind of process, well, of course, probably mathematics is not the right thing for you. Probably you should just finish the books and then basically get to the thing that you enjoy the most. Probably that's what you should do. But this is mathematics, and basically while you're doing this kind of thing, which seems to be seemingly unreasonable because the result is already there, but while you're going through all of these steps, what you're doing is actually nothing but mathematics. So anyway, enough of philosophy. Now I can write this as, basically add these two together, so I can write this as sigma of p of basically omega of I for all omega of I belonging to the set basically A intersection B. And then again I can do the same thing over here, because these were A intersection B and B minus A. These are also disjoint sets, so you can add them together, meaning separate them and add them together. So you can write this as, for example, you can write this as sigma of P of omega of I for all omega of I belonging to the set, for example, A intersection B. And add to that again sigma of P of omega of I for all omega of I belonging to the set, for example, B minus A. Belonging to the set B minus A. And that's basically the whole thing here. And so using one, we said that the sigma of P of the omega of I for all omega of I belonging to the sets A minus B and A intersection B and B minus A. If you add all of these together, you will get P of A union B. So what that means is that A minus B is over here, A intersection B is over here, and B minus A is over here. So I can write all of these three added together. I can write it as P of A union B. So that means that, so now I don't know what actually I had started with. This is P of A plus P of B. So that means that I can write P of, and let me change this color. So that means that I have P of A plus P of B is the same thing as P of A union B, which is basically, this is using one over here, and then we have this part over here, which is plus basically sigma of P of basically omega of I for all omega of I belonging to the set A intersection B. So, and you can write this as basically P of A intersection B. So that means that then P of A plus P of B is the same thing as P of A union B plus P of A intersection B, right? So what that means is that then, hence you can say that P of A union B is the same thing as P of A plus P of B minus P of A intersection B. And that is the result that we were looking for. And also we can use a Venn diagram to basically do the same thing, which we will do as well. Okay, so now to prove the same thing, using a Venn diagram, what you can do is that basically, alternatively, it can also be proved as follows, that basically A union B, this is A union B, is equal to A union B minus A, because so B minus A is basically this part, and And of course you can say that A union B, which is basically this whole part over here. So this whole part over here is basically A union B, right? Now A union B is the same thing as A, which is this part over here, union with A union with B minus A, which is this part over here, which of course makes sense. So you can say A union B is the same thing as A union with B minus A, where A and B minus A are mutually exclusive, where A and B minus A are mutually exclusive, and B is equal to, and you can write basically B, and you can write B is equal to A intersection B, which is basically this part over here, union with B minus A. So you can write it as B intersection or A intersection B. So you can write B is equal to A intersection B union with B minus A. Union with B minus A, right? So this is A intersection B, this is B minus A. So when you put them together, you'll get B, of course. Where A intersection B and B minus A are mutually exclusive. Where A intersection B and B minus A are mutually exclusive. Are mutually exclusive. So using axiom 3 of probability, we get, using axiom 3 of probability, we get, so axiom 3 of probability was basically, we had 3 axioms in the beginning of this section, which were basically, if E and F are mutually exclusive events, then P of E union F. So the axiom 3 of probability was basically, if E and F are mutually exclusive events, was if E and F are mutually exclusive events, then P of basically E union F, is equal to P of E plus P of F. Of course, we did not actually prove this, but, well, of course, I mean, you could say that, it makes sense. I mean, it makes logical sense that, well, it makes logical sense that P of E union F is the same thing as P of E plus P of F. Of course, provided that these two are mutually exclusive, meaning that E and F are mutually exclusive. Otherwise, that's not true, right? So we said that if E and F are mutually exclusive, which is of course the condition is there already, mutually exclusive events, then P of E union F is equal to P of E plus P of F. So that was basically the third axiom of probability that we did here. Now, if I basically write, so now using the axiom 3 of probability we get using this situation that I have here. So this is A union B, right? So that is A union B minus A. So then you can write that, you can basically write this equation over here as P of A union B. You can write it as P of A plus P of B minus A based on this. P of A plus P of B minus A. And you already know that these are mutually exclusive events, so you can basically write this expression and so I call this equation number 2. I don't know how this color changes. I mean, it does it. It's doing everything on its own. It seems that it's automatic or something. And P of B here and P of B here by the same logic is equal to P of A intersection B, and both of these are again mutually exclusive. So I can write P of A intersection B plus P of basically B minus A plus P of B minus A, which is basically equation number 3. And somewhere over here we had equation number 1 as well, which was, I suppose, I don't know where it was. Okay. It was in the beginning of this whole section. So if you subtract basically 3 from 2, subtracting 3 from 2, you will get P of basically A union B minus P of B is equal to P of A plus P of B minus A minus P of A intersection B minus P of B minus A. So P of B minus A, P of B minus A, you can cancel out, and so you will get P of A union B is equal to P of A plus P of B minus P of A intersection B. And of course, the above result can further be verified by observing the Venn diagram in this figure, which is basically, if you have a Venn diagram here, you can use a Venn diagram as here. So you have basically your set A here, you have your set B here, and this is basically this part over here is A minus B. This part over here is B minus A, and this part over here is A intersection B. This is A intersection B, and the whole part over here, meaning that meaning that basically this whole part over here, this whole part over here is basically A union B. So as you can see, this is P of A union B. You can see that A union B would be the same. Basically, this whole area you can see over here is equal to P of A, which is this part over here, plus P of B, which is this part over here. And you can see that we have counted this intersection already twice. So I have to subtract that from the result, meaning that then I will come up with the same thing, meaning that P of A union B is the same thing as P of A plus P of B minus P of A intersection B, which is the same thing. Now if A and B are disjoint sets, that is they are mutually exclusive events, then A intersection B is the null set. Now of course if basically A and B, if basically A and B are disjoint sets, that is they are mutually exclusive events, that is they are mutually exclusive events, then A intersection B is equal to the null set. Then of course A intersection B is equal to the null set. Therefore P of A intersection B is equal to 0. And thus for mutually exclusive events A and B, exclusive events A and B, we have P of A union B is the same thing as P of A plus P of B, and we don't really have to write P of basically minus P of A intersection B, because this is already equal to 0, so you don't have to subtract the 0, which is axiom 3 of probability, which is axiom 3 of probability. So that's basically the whole story here. Now, of course, not the whole story. There is still a couple of things to say. The next thing that we will discuss is probability of event not A. So I'll see you in the next video.